Hello, it's Keith here, and this is lesson 69 of the platform-specific series of my 650 assembly programming tutorials. And we're looking at the NES, and we're looking at music. We're looking at using the interrupt handling and playing music. We're playing music with my ChibiTracks music player, and we're playing the Chibi Akamas theme here. And this is the previous Mintal example, which had a simple graphics animation running on the screen, as you can see, and this was copied off other systems. That's covered in a separate tutorial, though. What we're looking at today is it's an overview of the interrupt handler and just discussing how my music player can be used on the NES to play music, as you heard. So let's go over to the source code and let's take a peek. Now, we have covered interrupts before, but I thought it was worth going over again. We have to, of course, use interrupts as part of our general graphics routines because on the NES, we can only transfer graphics data to VRAM during the VBlank, which is the interrupt we're going to be using to time our music today. Now, as with most 6502 systems, the NES actually has the vectors, that is the addresses of the interrupt handlers at the footer area. Memory address FFA, we have the NMI handler, and that is the interrupt handler for VBlank. So we just specify the address of the routine, and we're running NMI handler here. We also have one for the IRQ here, IRQ handler, but that is actually a dummy one. All that does is that just links straight to an RTI command. RTI is return from interrupt. That pops the flags off the stack and then returns, so the flags are backed up and restored for us automatically by the interrupt handler. Now, the main interrupt handler we're going to take a look at in a moment, that's the NMI handler, and that's what's going to do our graphics and our sound. Now, just because we've set up the address of the interrupt handler doesn't mean the interrupts are going to occur. Now, what we need to do to enable the interrupts is very straightforward on the NES actually. All we need to do is we need to set bit 7 to 1 and write that to memory address 2000 in hexadecimal there. That controls various things, but the one that we want is the NMI on VBlank, and that is the top bit 7 there. So we're setting that to 1 and writing that value there, and that will actually turn on the interrupts if we disable this line. So we don't set that. Then when we run, we actually won't get any graphics either because, as I say, the graphics routine is actually part of that VBlank interrupt. Now, the graphics are actually being held in a cache of sorts. I've actually covered that. If you want to see how that works, please see the Mintal series or my other series that have covered that. But basically, we need to cache the data that we transfer. Now, our interrupt handler has two things to do basically. Firstly, it needs to transfer the video data, and secondly, it needs to update the music. We need to update the music during VBlank because we need that consistent timing that runs at the same speed irrespective of what else is going on in the program. However, the music can be updated at any time. It doesn't need to be done during the VBlank procedure. The VBlank is, of course, when the CRT beam is not drawing the screen, so at the end of every screen and just before the start of the next screen. Our music can be updated actually in the middle of the screen, but our video data cannot be transferred any time other than the time that the beam isn't redrawing the screen. And the important thing of that is we need to draw our screen first because that's the more time sensitive part of the equation. So what we're doing here is we are starting at NMI handler. We are pushing the accumulator and the Y register onto the stack here. We're going to use Y during this part, and we're checking if there's any VDP data to update. And if there is, we're transferring the data to the video hardware. We're repeating until we've transferred the maximum possible number of bytes here. And then once we've done that, basically, we need to reset our scroll position because that is important. As part of writing data to VRAM, the scroll position gets reset. We've got some code here to do a DMA transfer of the sprite buffer here, if we are using hardware sprites. And then once we've done all of that, we can then start worrying about the other stuff, which is, in this case, our music. Now, ChibiTracks uses the X register as well as the Y register in the accumulator, and it uses various zero-page entries here. I use the zero-page, like Z80 registers, because ChibiTracks is ported from the Z80, so we use two 16-bit pairs, HL, DE, B, C, and IX. So each of those are named pairs, and I've got a macro here to push a pair of zero-page entries in one go. That just makes it nice and convenient for porting the Z80 code. ChibiTracks Play updates the music player and sends the new settings as required to the sound hardware. So it will look at the next line of the patterns within the music file, and it will update to the hardware accordingly to make sure it's playing the right sounds for that line of the pattern. So that's what that does. Now, when it comes to actually getting ChibiTracks working, there's only a few things we need to do. We need to include various ASM files. ChibiSound Pro is the platform-specific driver, so that would be the NES-specific driver in this case. There's one for each system that actually handles the platform's particularities of the sound hardware. The rest is multi-platform. ChibiTracks is the main music player. Fraction 16 and ChibiTracks Tweener are the calculation code for calculating the in-between notes. I'm planning on reusing those in other systems, in other code. That's why I've split them out. So ChibiTracks is the music player. And of course we've got a song. Here is the song. Chibi theme.cpt is the file we're playing today. Now ChibiTracks and Chibi Sound need a little bit of memory, so they need around 128 bytes. It varies a little bit depending on the system because of the platform specific peculiarities, but we need to allocate some memory, so we define Chibi Sound RAM here. And parts of that will be used for the music player, and we also need to define some variables for the song, so we're just defining pointers to that RAM here. So those are various attributes of the song itself. We don't actually need to set those up, those are all set up automatically for us. The values for them are automatically loaded in from the song file. Now we have a few options. Allow relocation is quite an important one. When we export a binary music file from the Chibi Tracker software that I wrote, the Windows application, we specify a load destination. So if we specified 8000 for example, that means the song is intended to be played from memory address 8000, and that's encoded within various positions within the binary file to tell it where to load the instrument list from and things like that. However, we may want to load to a different memory address, because if on the Spectrum we can't load at 8000, we might need to load at 9000, and that means we would have to re-export our binary file. That's inconvenient. So what we can do is we can allow relocation, and that will recalculate an offset and use that offset. It makes the player a little bit bigger, a little bit slower, but not very much, but it means that we don't need to re-export our file. I'd strongly suggest you have that enabled. Allow speed change is another option. This allows us to change the speed of playback at playtime. Now this makes the player a little bit bigger and a little bit slower, more significantly bigger and slower than the allow relocation, but not massively so. And this allows us to change the play speed, but alternatively we can disable this and we can pre-multiply the play speed when we export the binary file. That means the player doesn't need this slower extra option, but it means we can't change the play speed. And the reason we might want to change the play speed is if our system is 60 Hz and our song was encoded for 50. For example, if I play the song here, if I re-enable the interrupt and play the song here, just forgot to disable my example code earlier. So that is roughly speaking the speed that it should play at. Now this is a 60 Hz system, and so if I disable that speed override, that's actually playing a little bit fast. And so by enabling the allow speed change, we can alter the speed at playback time. And in this case, we can override the 50 Hz playback speed and slow it down a little bit for the 60 Hz playback speed. And you could do this as well if you want the game to get faster and the music to get faster and faster as the player runs out of time, maybe. Well, we can set a really low song speed. And you can see here it gets a bit crazy. So the song speed has potential benefits, but as I say, enabling that option does make it slower. The final option we've got here is the transpose option here. This is used for systems like the Master System, where the low note pitches aren't very well represented, and so we can shift everything up one octave, and that makes the music sound more like it should. The low notes are properly represented, but they're all shifted one octave up, so the pitch is wrong, but the song will probably sound better as a result. So it's up to you whether you want to use that or not. I thought it was better for this song because it has a lot of very low pitches. Now when it comes to actually initializing the music, we need to do a couple of things. We need to run Chibi Sound Pro init. That initializes the sound hardware for this system, so that will do the NES specific stuff that's required. We then need to load the 16-bit address of the song we want to play. We want to play song 1, so we load that into song base here. We run ChibiTracks start song. That initializes all of the attributes, namely these ones, from the song. They're all in the binary file. In this case, we're overriding the song speed though, because we wanted to play it super fast in this case. And then that's all we need to do. So once we've done that, we just start our interrupt up, and the final thing we need to do is just update the music, and we do that in the interrupt handler with this ChibiTracks play. And of course, if you were doing something very simple like a title screen and you just had a thing saying press 5 to start, you could do this without interrupts. You could just have a simple loop to effect a delay, but obviously interrupt handling is going to be far more efficient at keeping the timing accurate. If your game is getting slow, the interrupt handler will still run at the same time, so that's going to be best if it's an option. Anyway, there we go. That's all we got to cover today. As always, go to my website, download the source code and the build script. You can also download the ChibiTracks music software and have some fun with it. You're welcome to do all of it, use any of it in any way you want. The ChibiTracks music software for Windows is also open source, so you're welcome to modify it if you so wish. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.